Hi, in this video, which is a follow-up of my last video about limits, I'm going to talk about colimits in infinity categories. So I'm going to explain how colimits are defined, how they can be computed in the infinity category spaces, and we're going to prove some very important, or at least sort of indicate some very important results, how one colimits of very complicated shapes can be reduced to understanding colimits of much easier shape. As the last lecture, in general, this course on infinity categories is not meant to give you a throughout grounds of definition course on infinity categories. It's rather meant to give you like a working feeling of how to work with infinity categories, because later we're going to dip into the more complicated parts, higher algebra, ring spectra, and all of this was meant to be, or is meant to be, in support of our course about topological cyclic homology, where many of these concepts will be used. Okay, so let's recall that last time we introduced the notion of a limit. So we had a functor from f from a simplicial set to an infinity category, and the limit is basically uniquely characterized by the universal property that maps into the limit I and I f of I are equivalent to maps of functors from the constant functor x, from an object x in C into f. And in the end we've seen that this is also equivalent to just saying it's a limit in the infinity category of spaces of maps in in C from x into f of I. So this mapping space then becomes a diagram in spaces, and the mapping space is just the limit over that. So we've really made this precise in the case that C was a homotopy coherent nerve of a Kahn-enriched category. But in fact, I mean, it turns out every infinity category is equivalent to that. So we'll use this formula for every infinity category from now on and sort of be a little bit vague about how this is a functor. Again, make this precise by assuming C is a simplically enriched category. And so what we're going to do today is we're going to talk about colimits. And the notion of colimit is just a dual of the notion of limit, so you can just reverse all arrows, and as usual there's a systematic way of doing that. If C is an infinity category, then there's another infinity category denoted C op. And what is C op? It's just the opposite simplicial set, by which we just mean as a functor from delta op to sets. It's just given by sending delta op to delta op. There's a self map op, which takes a linearly ordered set and equips it with the opposite ordering, and then you can just precompose that with our C. And it's a little observation that if C is an infinity category, then so is C op. And then one could just define a colimit of f I C as the limit of the opposite functor f op from I op to C op. But let me spell out explicitly what this means. Implicitly, I guess first you have to say a cone under your given functor f is an object y in C together with the transformation with a natural transformation eta from f into the constant functor on y, and then as in the case of limits, this is by definition, this is a colimit cone if for any z in C we have that the map in C from maps y into the mapping space in the functor category C to the I from F into ZC, which is basically given by composition with eta. So I guess really it's given by first sending a map y to c, so the constant map, the transformation of constant functors given by the constant map, and then post-composition, pre-composition with eta. This is an equivalence, a homotopy equivalence of Kahn complexes. And now, of course, all the statements we made about colimits, limits have analogs for colimits. One thing I want to note is, in a second I'm going to talk about how colimits in the infinity category of spaces look like. And that's not quite obvious how the formula we gave for limit in the infinity category of spaces can be dualized. So one of the major things I'm going to do today is tell you how colimits in the infinity category of spaces look like. And first of all, but let me note, there was this proposition that in the infinity category of spaces, limits can be detected on pi naught. So you don't need to check that this is an equivalence of spaces in this case, but it's enough to check that on pi naught. And the dual statement is also true. So let me state it like slightly differently than the other statement. So extending an object y in the infinity category of spaces to a colimit cone over some fixed functor. I mean, the functor is prefixed f from I into S is equivalent to providing, I was just wondering about the correct nerve, but a verb, let's say providing a natural isomorphism between homotopy classes of maps y to z in C, for any z, and I want to provide a natural isomorphism of that to just in the functor category homotopy classes. So in other words, just this on pi naught, and this is natural in Z. And here I have less problems, because once I pass to homotopy classes, it's pretty easy to see that this is actually both are natural in C. So these are functors in Z on, I guess, formally speaking, the homotopy category of C, but actually I guess I was going to say spaces. Sorry, this was meant to be a statement about spaces. Yes, and so this is pretty helpful because it also tells you that you can check the universal property of colimits on pi naught, and the proof is the same as before, basically, just the dual version you equip like mapping objects to see that this being an iso on pi naught, this implies that for every further object mapping into it, it's an iso, and then by some exponential law, and then you're done. Okay, so I just wanted to have that on the board so that we can use this. And now let's go through some examples. So the first example is if I is an empty category. Then I guess again the colimit over I. So a functor from I to C is no datum at all. For every infinity category, there's just a unique functor from the empty set. And so a colimit over I is equivalently a colimit over the unique functor from I, and we call that initial object. Initial object, as usual in ordinary category theory. And what is the universal property? And we write it as empty set. We use this empty set notation, and then the universal property is just that maps out of the initial object into any other category object is just contractible. Okay, so that's what an initial object is, and of course in the infinity category of spaces we have, I mean, the initial object is the empty space. So this suggestive notation is true now. As a second example, I want to cover coproducts. So if I is discrete, so I'm going to confuse again the underlying discrete set and the simplicial set obtained from that, which is constant, then a functor is just given again by a family of objects y indexed by the underlying set of I, and then the colimit over such a thing is called coproduct, and we write it as the disjoint union over the yi's. So that's our notation for the colimit of f. And what is the universal property? The universal property just translates into that maps of C from this coproduct into any object Z is equivalent to the product of the mapping spaces I and I map in C yi, Z. As usual. And again, in S, we have that the coproduct I in I over spaces yi is the usual coproduct, is the disjoint union of Kahn complexes. Okay, so that is the case of coproducts and the initial object. And again, of course, the initial object is a special case of coproducts for I being empty, but it very often plays a little bit of a special role. And now we want to talk about pushouts. And so what is the indexing category here? For pushouts, the indexing category here is just going to be this one. This depicted like this. So this is like an ordinary category, it takes a nerf, or you can define it as a simplicial set. It's just a pushout delta 1 over delta 0 of delta 1, a pushout in actual simplicial sets. And then a functor f is just given by a diagram in C of the form A, B, C. Okay, and what is the universal property? Now I'm using my sort of formula from the beginning. The universal property is that for any Z we have maps in C from, I guess maybe I should sort of invent some notation first. Let me maybe erase that. So first of all, if I have such a colimit over f, I will write the colim over my f. I will write this with the usual pushout notation. So I'm going to write pushout over A with C. So that's my notation, and then universal property. The property for any Z in Z, we have that maps from this pushout, I guess B pushout over AC into Z, is actually equivalent to just the pullback in spaces, map C, B, Z times over map C, A, Z, and this is map C. C, Z. And this is actually the pullback in the infinity category of spaces. So it's not the actual pullback of topological, of Kahn complexes. I guess I've been sort of a little bit confusing possibly at some points, where I sort of sometimes wrote pullback and pushout and meant the one in actual simplicial sets. But here this is really the pullback in the infinity category of spaces. So in other words, the map out of this guy into any D is given by a map of B in Z, a map of Z in C, and a homotopy, witnessing that the two composites are the same. And in general, you don't want to, I mean, you can't even say what it means that this homotopy is the identity. Remember, in an arbitrary infinity category, we just don't have a way of sort of talking about actual composition on the nose. So that's kind of, in some sense, the only thing we could possibly demand. There is no stricter notion of pushout in an arbitrary infinity category. That's actually a very important case. So somehow once you write down these concepts in the right generality, you can't even determine, I mean, sort of write down too strict definitions because they wouldn't make sense anymore. Okay, so now I guess what are pushouts in the infinity category of spaces? And pushouts in S are given by the usual formula a lot of you might know from the topology course. So let's see how this works. So given a diagram A, B, C of Kahn complexes, spaces. So recall spaces meant for us equivalently Kahn complexes. So we form the following simplicial set. And now this is an actual simplicial set for the moment. I guess I'm overloading notation now. I don't want to. So we form the pushout over, I guess, A cross 0 with the simplicial set A cross delta 1. And then we form the pushout over A cross 1 with C. Right, this just means, I mean, this is just A cross delta 0, but I'm just writing 0 so as to indicate the map into this delta 1. So I'm forming this pushout. And I guess some of you might have seen this. This is called, in topology, this is usually called the double mapping cylinder. And why is that? That's because, I mean, the picture that, I mean, if you do the same construction in topological spaces, the picture is you form the mapping cylinder A cross delta 1. I mean, you form the sort of cylinder on A cross delta 1, and then you glue B here, and you glue C here. That's why it's called the double mapping cylinder. And again, I don't want to introduce some underived notation here, but this is just the actual pushout in simplicial sets. And then what I'm going to do is I replace this guy by a Kahn complex, dk, d. Right, so this is a priori only a simplicial set, but recall spaces meant for us Kahn complexes. So what I'm going to do is for every simplicial set, there's a universal way of replacing this by a Kahn complex. This is just done by, I guess, for this to be a Kahn complex, it would need some fillers. So what you're going to do is you just check for every diagram horn in here which doesn't have a filler, you just glue in the filler, and then you keep doing that. And if you do that always like iteratively for those horns which don't have filler, this leads to a unique Kahn complex. Okay, and so here you replace this by a Kahn complex, and then the statement is then this diagram, the resulting diagram A, B, C, dk in S is a pushout. And here, note, my convention I had before, if I write such a diagram in an infinity category, that means it comes with a canonical homotopy filling that, or which is the map from delta 1 cross delta 1 to S. And here it's really true that if I go from A to D, or maybe from A into this guy, actually the two maps are not equal, right? If I go into both summons, they're not equal, but they will sort of differ by the homotopy. I have sort of glued in the universal homotopy. So this is really like one of these like commuting up to homotopy squares, and then this is a pushout. And this I want to leave as an exercise at this point. So I guess this really boils down to checking this universal property, and I guess using the exercise we had last time, how pullbacks in spaces look like. So this is really mapping out of that. I guess I'm almost spoiling it now, but mapping out of that really on the nose produces this kind of homotopy pullback we've written down last time. And now we've seen that the infinity category of spaces admits arbitrary coproducts and pushouts. Our next goal is to show that the infinity category of spaces has all colimits. And by all colimits, again, I mean really all colimits for functors indexed on a small simplicial set I. I guess I didn't really talk about set theoretical issues, but it's always going to be all colimits over small I. If you have a large infinity category which has all colimits indexed over large infinity category, large simplicial set, that actually would pretty much force it to be a poset. like in ordinary category theory. So this can't happen for set theoretical issues. Okay, good. So there's basically two strategies now how to reduce the existence of all colimits in the infinity category of spaces. So one strategy would be basically the dual of the strategy we did for limits. So you write down a formula for an arbitrary colimit. I mean, there's a bunch of ways of doing that. There's the so-called Bousfield-Kahn formula, but I guess you can also somehow, I don't really want to do that, but let me put it in brackets. So if you have a functor from I into the infinity category of spaces, the colimit can basically be written as, you just take the pullback over spaces with pointed spaces. And I guess then you have to take the Kahn replacement of that, because this is a priori not a Kahn complex. And I guess, so you have to be a little bit careful what pointed spaces here means. You have to make it happen that this is actually a fibration S star over S, which might not be the case in terms of our definition, but let's not worry about that, since I'm not going to employ this formula anyways. Instead, I'm going to follow a different strategy. So there's a different strategy, and that is actually one proves abstractly that whenever an infinity category admits all coproducts and all pushouts, then it already has all colimits. And that's what I want to do today, and because this is not only in this situation, but in general a very important way of understanding colimits. And somehow the proof will not just be like an abstract proof, it will be very constructive. So it also tells you how to compute an arbitrary, it basically gives you a formula, how to compute an arbitrary colimit in terms of pushouts and coproducts, which we now understand in spaces. But let me first sort of explain that strategy in some easy examples. So examples of this kind of thing I'm going to do in general now. And that is, first of all, I guess, I haven't really talked about that, but a coequalizer is a colimit over the diagram, which is the following diagram. It's just a nerve of an ordinary category as well, with just two objects, 0, 1, and two morphisms from 0 to 1. I guess one way to write that is I guess you can write it as a disjoint union over two one simplices, and the equivalence relation is you glue together the start and end points. So and then a colimit over that is a coequalizer, right? And so how would a coequalizer look like? It would just be if you have, a map, a functor out of that into any infinity category is just something looking like that. And then a coequalizer is basically the universal fork here. So the universal morphism which receives the map that with a homotopy of these two composites, and so map out of that are the same as sort of maps out of B with homotopies between the composites. That's what a coequalizer is. And so the claim is, we claim that the coequalizer is the pushout, is always the following pushout. So you take a coproduct A. So I guess here I'm assuming that C has all coproducts and pushouts, and I want to tell you how to write the coequalizer. So what I always have is A disjoint A, there's a codiagonal. What is that? That's a map universally corresponding to taking the identity on both functors. So remember, maps out of the coproduct are the same as pairs of maps, so I just take the identity comma identity. That gives me what is called the codiagonal. And then I have two maps into B here, right? I guess if I denote these maps F and G, this is just F comma G. Again, universal property of coproduct, this corresponds to two maps to B, and I'm just taking my two maps. And then the claim is that always C is the push out of that diagram. And that's a claim which is very easy to verify now. So I guess the assumption is that whenever you have a coequalizer and coproduct, then this is a pushout. And vice versa, when you form the C as being this pushout, then it's also this diagram is a coequalizer diagram. And in order to check that by what we've done so far, you just have to map out of it into any object and then check the dual diagram in the infinity category of spaces. I guess the dual concept of a coequalizer is an equalizer. So that's a good exercise at this point to just carry out this little computation that in the end you're just going to check something in spaces and then it comes down to a pi naught computation. Okay, so that's the way you decompose an arbitrary coequalizer as a pushout. But the converse can also be done. So I'm claiming that in general a pushout A, B, C, D, right? So D being the pushout of the upper left diagram in my infinity category 3 can be written as a coequalizer. And how? So what I'm going to do is I'm going to form the coequalizer of, I have two maps from A into B disjoint C. So again, under the assumption that coproducts exist. And what is that? I guess I have a map from A to B and one to A to C, and I can just post-compose with the structure morphisms of the coproduct. That gives me two maps here. And the claim is that D is a coequalizer of that diagram. And again, this in the end amounts to checking that maps out of this D are the same as, I guess from the universal property of the coequalizer, are the same as maps such that the two composites agree, and that's also the universal property of the pushout. Okay, so that is how we can translate colimits and coequalizers into each other. And now there's the third colimit that is important, that is the sequential colimit. Sequential colimit. So this is the index in category I is delta 1, disjoint delta 0, delta 1, and so on. And I talked about this last time in the context of limits. Unfortunately, there I was missing an op. In the case of limits, it should have been the opposite of the simplicial set that I was talking about. But so we explained that this simplicial set is basically, I mean, if I make it into an infinity category, this would just be the nerve of the natural numbers with the less or equal ordering. But I'm going to use this slightly smaller simplicial set, so everything is somewhat more tractable and understandable. And so this is a sequential colimit. So I guess this is just a sequential colimit. I mean, a diagram just consists of a bunch of objects with morphisms in between them, and then the sequential colimit is just y infinity. So we write this as colim like this of yi. So y infinity is just the suggestive notation for this sequential colimit. And the claim is that I can write this sequential colimit also in terms of coequalizers and coproducts. And how do I do that? So the claim is that I do I larger equal 0, so through the natural numbers, and I do the disjoint union yi again, I larger equal 0. And then the point is I have two maps from here to there. Namely, which maps do I have? I have first of all the identity, and second I have the shift map. So what does the shift map do? The shift map will just send yi by means of the universal map to yi plus 1 here. Right, so again, in order to provide such a map, I just have to tell you how to map out of the respective summands. And here I'm just going to say the I summand is sent to the I plus first summand, to the inclusion of the I plus first summand here by means of this map. And so then the claim is that this y infinity is a coequalizer. And vice versa, whenever I form this coequalizer, this will automatically be the sequential colimit of the upper diagram. And again, this amounts to checking what maps, what cones under this diagram are, and that this is the same as cones here. Okay, so that is how we translate coequalizer, sequential colimits, and pushouts into each other. And in order to state the general result, let me first introduce a bit of notation, definition. So simplicial set I is called finite if it has only finitely many non-degenerate cells, generate simplices. And a colimit is called finite if the indexing set I is finite. And one has to be a little bit careful if one starts contemplating finite. I mean, we're not going to need this, but let me just warn you that once you start contemplating what a finite infinity category is, you maybe want to say it's obtained from a finite simplicial set by replacing this by an infinity category. This might, of course, a priori result in something which has more than finitely many non-degenerate simplices, but again, this is our notation for simplicial sets, and we're going to work with these smallish guys here. So under this convention, this guy here would be finite, but again, I'm not going to need this now. Okay, sorry, this would not be finite, of course, but I guess every truncation of it would be finite, sorry. Okay, which is fine, I guess. Anyways. So the theorem I want to allude to is the following. So that's the following theorem. For an infinity category, C, the following are equivalent. 1. C admits an initial object and pushouts. 2. C admits all finite coproducts. So for a coproduct to be finite, this just means the indexing set is finite. All finite coproducts and all coequalizers. And 3, C admits all finite colimits. So again, admitting a class of colimits just means for every functor there exists a colimit. Okay, and let me give you an idea, a sketch why this is true. So kind of, again, proofs are semi-rigorous here. So first of all, I guess we have to see that 1 and 2 are equivalent. But so the first thing is to note if you have 1 in order to reduce 2, so you have to check that it has coproducts. So a coproduct A disjoint B is just a push out from the empty sets, the initial object A and B. So once you have an initial object and pushouts, you also have binary coproducts and then inductively all coproducts. And so also we have seen in the previous example that coequalizers can be obtained from pushouts and coproducts. So that is 1 implies 2, and for 2 implies 1, you just have to note that the empty set is a coproduct. Right, the empty coproduct. And then the previous exercise where we have seen how to, the previous example where we've seen how to translate pushouts to get pushouts from coequalizers. So that shows that 1 and 2 are equivalent. And now obviously 3 implies 1 and 2 because all the colimits involved are finite. So the hard step in this proof is how to form an arbitrary colimit, finite colimit from pushouts, coequalizers, and coproducts. And for this, I'm going to give you an idea how this is done. So again, this is also constructive. So it gives you in principle actual formulas. And basically, the usual formulas you might see in courses about homotopy theory, the so-called Bouwschild-Kahn formulas, are basically instances of that. So what you do is if I is an arbitrary simplicial set, is a finite simplicial set, what you do is it has a skeletal filtration. So you can write I as a union of its skeleta And because it's finite, some scalar, say in, will be I. So where say n is a dimension, it's called the dimension of I, the dimension of the simplicial set. And how is in obtained from in minus 1? So it's obtained by attaching cells. So this is the simplicial version of CW complexes. And what does it mean to attach cells? This just means you have a bunch of cells. These are just the non-degenerate n simplices. That's over some indexing set j. And that they are attached along their boundary to the n-1 skeleton. So we have actual pushouts of simplicial sets like that. And now the point is, in general, in such a situation, in such an attaching situation, you want to compute the limit. So I have my functor f from my simplicial set I into C. And the point is now that the claim is that the limit, the colimit over I of f is equivalent to the pushout of the colimit f over in. And then you form the pushout over the colimit. And this is in an arbitrary infinity category. So here I really mean the homotopy pushout, the pushout in the infinity categorical sense. I was almost saying homotopy pushout. I was trying to avoid that here, but okay, now I've said it already. So the colimit over the restriction of f to this part of the diagram, boundary delta n over j, I guess. And I guess this is now the colimit over boundary delta n, this simplicial set, and here I have the colimit, and here I should have put n-1, sorry. And here it's the colimit over disjoint union delta n, and here's also disjoint union over j. Sorry, I hope this formula is still readable. It's just I was just trying to copy what is standing here. Disjoint union delta n, and then f restricted to disjoint union delta n. And here I also have a disjoint union. Okay, and that is a slightly non-trivial statement here. So we're actually sort of using something here, namely that this is a monomorphism of simplicial sets. And you can deduce that from the universal property by certain lifting properties. I'm not going to do that. I'm just going to tell you that once you have such an attaching a cell square, you get that the colimit decomposes. And that's again to be read the same way that we talked about coequalizers and pushouts. So once you form the right-hand pushout, it forms the colimit of the left-hand side. Right? And then somehow the point is that, moreover, here we have this huge disjoint unions, but it turns out, of course, if you form a colimit over disjoint union, say of the boundary delta n's, say the boundary delta n's of any functor g defined on this disjoint union, first of all, it's always going to be the coproduct over the respective factors over, say, j, and this is indexed over j, of g restricted to the j's guy, j. I guess it's really delta n, but the delta n of j. And then the next claim is that you're forming a colimit over the simplicial set delta n. That is just actually given by evaluation at the nth guy. So g restricted to delta n of n. And why is that? That is because delta n as a simplicial set is the nerve of a pose set which has a terminal object. So it's a little exercise to work out that if you have a pose set which has a terminal object, or more generally a category which has a terminal object, and you form a colimit over that guy, then it's just given by evaluation on that terminal object. And that basically follows immediately from the universal property once you say it correctly. So in that case, we see that under our assumption, this part of the colimit just exists, right? Because this is just indexed over this disjoint union delta n's. And so in order to prove that this exists, we had reduced to show that those exist. The point is those have strictly smaller dimensions, those simplicial sets. So now our proof in order to show that all finite colimits exists under the assumption that pushouts and coproducts exist will be a proof over by induction over the dimension of I, and this is the induction step. The first step in the induction is easy, because then we're zero dimensional, we're disjoint unions of points, so it's coproducts. Okay, and that finishes me giving you the idea of the proof of why arbitrary finite colimits exist. From this statement, we can already conclude that the infinity category spaces has all finite colimits, right? Because we have already shown that it has an initial object and pushouts. So we know already at this point that it has all finite colimits, but we want more. We want to say that it has all colimits, and that's a variant of the last theorem, which works for infinite colimits, and that's the following variant. So if an infinity category C admits arbitrary coproducts, right? So not finite coproducts, but arbitrary coproducts. Then the following are equivalent. So that's 1. C admits all colimits. All colimits. 2. C admits pushouts. And pushouts are, of course, just a diagram consisting of 3 objects. Not any fancy infinite version of pushouts or so. So C admits coequalizers. And 4, C admits geometric realizations. That is colimits indexed over delta. The category delta op, the simplicial indexing category, and then the nerve of that. Okay. So that's a general statement, and again I want to give you an idea of how one proved this. So I guess proof again 2 and 3 equivalent is just as before. We have already seen how to translate pushouts into coequalizers, and I guess 1 implies all the others is obvious. Say 1 implies 2 is obvious. And 1 implies 4 is also clear. So now there are 2 cases left, so we have to write an arbitrary colimit. So let me first tell you how 2 and 3 together imply 1. So we already know 2 and 3 are equivalent, so I don't have to think about which exactly implies 1. We'll see that. So we're basically copying the strategy we had in the last proof. So we write an arbitrary simplicial set I as the union of its skeleta. I0, I1, I2, but except in this case now we might have infinitely many. So in every step we might have to attach cells, but anyway, we can still write it like this. So it's an infinite union of its skeleta. And then again, like if we assume that our infinity category has all pushouts and all arbitrary coproducts, by the same argument as in the last step, we can show that the colimit as we restrict to all the skeleta exists. So now the only question is how do we get to I from its finite skeleta? So we have I is actually itself. So the claim is that the colimit over any functor over I is actually the same or equivalent or can be formed by the colimit over the natural numbers. So the sequential colimit of the colimits of f restricted to In. And that is over In. So I'm claiming that, and again this is a check in universal properties, that the colimit over this I is just the sequential colimit over the colimits f restricted to In, which we already now know exists. And then again we've seen how we can translate sequential colimits into coequalizers. And then this finishes the step that 2 and 3 imply 1. And so now the last step you have to contemplate is why 4 implies, and I guess I want to go from 4 to 2. So I admit that there could have been a better ordering of 1 through 4. Anyways, so I want to show 4 implies 2. So I guess now I have to argue if colimits indexed over delta op exist, that also pushout exist. And this is just, I guess here I'm going to be very sloppy, even more sloppy than before, but again, this is just meant to give you an idea how to do these things. So if you have a pushout like this, A, B, C, so you want to form the colimit of a pushout like this, the claim is that this is, the pushout, D, is the colimit, D is the colimit, the pushout is the colimit of this following simplicial diagram, where you form B disjoint C, and then I have B disjoint A disjoint C, and there are 2 maps here, and these 2 maps are given by sending A either to B or A to C by means of the 2 maps, right? And on the other 2 factors, it's just the identity. And there's also a degeneracy map by just including B disjoint C into that. And then again, I have like a triple guy here where I put 2 copies of A, C, and so on. And for those of you who know what this word means, it's basically a 2-sided bar construction here. And then the claim is, as I form the colimit, so the first claim is this forms a simplicial diagram. That's actually not too hard to check. But then the claim is that the colimit over this simplicial diagram is the same as this pushout. And that is just because, one way to see that is this is left Khan extended from delta 1 less or equal 1. And then, the colimit is just somehow the coequalizer of that part. And then it's not hard to check that it's a pushout, basically as we've did before. Okay, so but once you acknowledge this fact that you can rewrite the pushout as this geometric realization, this finishes the proof. Okay. And an immediately corollary is that the infinity category of spaces, corollary, the infinity category S has all colimits. And it also, again, let me stress that this basically, in principle, gives you a formula how to compute all colimits. Not only did it show abstractly the existence. And I want to finish this lecture by, so far we've only talked about the infinity category of spaces, but of course now we're going to introduce many more infinity categories, and we're going to talk about colimits and limits freely in those other infinity categories. Let me just give you 2 of them here. So definition. So the infinity category as star of pointed spaces is the homotopy coherent nerve is n delta of Khan star, where Khan star is the simplically enriched category, simplically enriched category of pointed Khan complexes. Right, you just pick the base point and base point preserving map. That's again going to define for you a Khan enriched category. And then you just take the homotopy coherent nerve. And the second infinity category, which is very important, is the infinity category cut infinity of infinity categories. So far we've really only talked about an infinity category as a simplicial set. So somehow, so far all the categorical notions we did were just sort of point set things about simplicial sets. But then of course you can also form an infinity category of infinity categories. Categories is given by the following homotopy coherent nerve n delta of, let me maybe say cut infinity delta, where cut infinity delta is the simplicity enriched category, whose objects are infinity categories and whose morphisms so hom, the simplicial hom in cut infinity delta between two infinity categories. This is defined to be a subsimplicial set of what we called the functor category before, xy. And I mean, a priori you might think, let's take the full functor category, and that's actually a good instinct. But it turns out, I mean, remember we said everything for categories enriched in Kahn complexes. So what we're going to do is let this be the maximal Kahn complex contained in this guy. So for every simplicial set, you can form the maximal Kahn complex contained in that. So if this is an infinity category, this amounts to just restricting to those one simplices which are actually invertible. So it's kind of the subgroupoid, the higher categorical notion of the subgroupoid, and then this forms the Kahn-enriched category, and then we form the associated infinity category. So morally, what's going on here is really that the category of all infinity categories this wants to be like a 2 category, infinity 2 category, meaning that it has like non-invertible morphisms also at level 2, but we're just neglecting that fact and treating it as an infinity category. Okay, and then I guess now I want to write down a theorem. And the theorem is that cut infinity and pointed spaces have all limits and colimits. And one way to prove that is to proceed exactly as we did so far. So what you can do is you can just figure out what pullbacks and pushouts are, and coproducts and products. So the point is that, I mean, coproducts and products are basically what you think they are. I mean, here you have to be a little bit careful about, the coproduct here is of course not the disjoint union. I mean, it has to be like the wedge product. But apart from that, it's just that, and here it's just disjoint union. So I guess I should point here and here. Here it's disjoint union, here it's a wedge product. Products are just the way you think. And then for pullbacks, you basically use the similar formula that we've used before. You have to be a little bit careful in the infinity category of infinity categories. You can't just sort of pull back over like the lower part to the delta one. You have to take equivalences in the lower part. And then you write down what the actual pullback is. And then push out the same, and that way you sort of can deduce the existence of all these colimits and limits. And let me end this lecture. There was this one really convenient thing when talking about spaces. And that was, in spaces we could just check whether something was a colimit or a limit on pi naught of the mapping space. And of course, this is actually some version of Yoneda. Once you know all colimits and limits exist, it's enough to check that something satisfies the universal property on pi naught. So basically, a posteriori, you can also prove that something is true here, but you can also use some sort of exponential tricks for mapping spaces, the fact that both of these simplicial categories have tensors and cotensors in the enriched category language to deduce that a priori. Okay. That does it for today. That finishes my discussion about colimits and limits. From now on, we're going to freely use the language of colimits and limits. This course was not meant to give you like a sort of completely rigorous formal introduction, but rather give you like a little bit of a working feeling for colimits and limits. So there's a lot of excellent literature where all of the steps I've done, probably in some permuted manner, are carried out in a more rigorous way, and which I really recommend. Thank you.